Here we will try to understand the intensities that we measure in XPS. So if we consider atoms in a thin layer D set at depth set in a sample, we can rate the contribution to the measured intensity as a product of different factors. First, there's the photoexcitation process. There's the peak attenuation due to inelastic electron scattering. There's the effect of the electron energy analyzer that specifies details of the efficiency of the electron energy analyzer. And there's a correction for angular deflection of electrons. We'll discuss these briefly, these different factors. For the photoexcitation process, we can use cross sections from tabulations, or we can use references. Usually when doing quasars analysis, we'll use reference spectra. For the attenuation, that's fairly simple. That's of course all included in the quasars analysis. And it comes about because due to inelastic scattering, the intensity of a peak drops exponentially with the path it's traveled in the sample. And the path is set divided by cosine theta here. And there's the inelastic mean-free path which enters here. Third factor is the electron energy analyzer as the efficiency of the detector, and there's the analyzer transmission function, which depends on the kinetic energy of the electron, so that should be corrected for, and that's what is done in the step where we correct for the analyzer transmission. It's usually fairly simple. Correction is usually sufficient to account for that. And then there's the angular deflection of electrons due to elastic electron scattering. Now this can be described conveniently by a simple factor here that you put on the expression where you make an analysis here which neglects elastic electron scattering, and then this corrects for that, for the elastic scattering effects. The origin of the effect for elastic scattering is that the electrons, if we ignore elastic scattering, they move out along trajectory A. But if an electron comes out here and we have elastic scattering up here, it can be scattered into the direction of the analyzer up here and be detected, but it will be attenuated less than the electron that's traveled here because the distance traveled in the sample is shorter. Can also go out initially in this direction, being scattered here, and be scattered out into the direction of the analyzer, and the path length traveled is longer, and therefore the attenuation will be larger for this electron than for the electrons that follow trajectory A. So this is an idea that Jablonski and myself suggested several years ago, in the late 90s actually, as a very simple way to correct for the effect of elastic electron scattering. And as you can see here, there's a cancellation effect here. So for thin layers, it turns out that the correction factor is small, less than 10%. For larger depths, it can be substantial, and also for larger angles. Normally we would not use large angles, would normally be within 45 degrees of the surface normal, so the effect of the angle here is usually not so critical. If we look at the effect as a function of depth, here's a calculation, Monte Carlo calculation of electrons traveling in silicon, copper, silver, and gold. So this includes both light elements and heavy elements, where you expect different importance of elastic electron scattering. It also covers a wide range of energies from 300 to 1200 eV. So that's the energy range that you normally look at in XPS. And what you see is that For shallow layers, actually, the correction factor is larger than 1. It's 5 to 10%, 5 to 15%. And this comes about because the electrons in the overlayer, if it's a very thin overlayer, the electrons can be backscattered from the substrate. So you actually get more electrons than if the substrate was not there because of the backscattering. And here we have the region of this competing effect. Some electrons travel a shorter distance, some a larger distance. So actually from depths from 0 up to about 2 inelastic mean-free paths, the effect of elastic scattering is less than about 15%. For larger depths, it quickly becomes substantial, and like a 3 inelastic mean-free path, it's like around 0.5. So this is a very simple way to make an approximate correction for elastic electron scattering.